Good evening, everyone. Myself Gautam Sharma. I welcome you all in a Sapience Education. So today I am going to discuss about the current electricity. This is the part for fourth video, where I will be discussing about the Kirchhoff's current law as well as Kirchhoff voltage. So let us discuss one by one. Okay. So here, what is actually the Kirchhoff's law? Is there Kirchhoff's current law? So what is Kirchhoff's current law? The algebraic sum of the current meeting at a junction in a closed electric circuit is zero. What do you mean by this? Any closed circuit where current is passing, so what happens, total current entering and exit will be equal to 0. See here, let us consider there is a current coming from any source which is I1, another current is coming in, this is I2, another current is going outside, another current is coming inside. So this will be I2, this will be I3, this will be I4. So as per this, see, it may be the possibility that the current is going outside as a 5. So as per this, what happened? Total current, sum of the total current will be 0. Sum of the total current means what? We have give the symbol. For example, if current is entering, so take it as a positive, and if current is going outside, so take it as a negative. So by using this, we have to add on. So let us, current is coming in, so I1 will be positive, so this will be positive I1, I2 will be positive, I3 will be negative, I5 I5 will be positive, it will be also negative because it is going outside, I4 is a positive. So finally total sum of the current will be 0, right? So this is the way you can go through this law. This is known as Kirchhoff's current law. See, in the more details manner, you can understand the incoming, the current incoming toward the junction are taken as a positive. Like this is your positive. I4 is going outside, it will be negative. I3 will be negative. I2 will be positive, and I1 will be negative, right? So the outgoing current away from the junction are taken to be negative. So by the Kirchhoff's current law, total current. So if you add on total current with the symbol, proper symbol, so this will be 0. So this is known as Kirchhoff's current law, KCL law. This is known as KCL law. Okay. Now let us go for next one. The Kirchhoff's current law is equivalent to the law of conservation of charge. What do you mean by this? See, if you think that current is, see, current coming and current going is not zero, so what will happen? See, a charge can't accumulate at a junction. The number of the charge that arrive at the junction in the given time must live in the same time. See, why we are subtracting? See here, the current is I1. You can use this figure backside. See, in this what happens? If current is coming, so we are taking as positive. It means that we are taking positive. Current is coming means what? Charge is coming. So let us consider 5 coulomb per second is coming. Here minus 2 coulomb is coming. So if 5 coulomb is coming and my 2 coulomb is going outside, so what will happen? 3 coulomb will accumulate. So if 5 coulomb is coming and it should go outside 5 coulomb. Let us see here. If the current is coming as I1, where charge is coming as a 5 coulomb, so what happens here? Here see, current has to go or charge has to go as a 5 coulomb outside. If this not happens, so what will happen? There will be accumulation of charge. Accumulation of charge. Okay. So if accumulation of charge will happen, so what will happen? There will be a spark. There will be leakage of the current. Okay. So here, as charge can't accumulate at a junction, the number of charge that arrive at a junction in a given time must live in the same time according with the conservation of the charge. If it does not happen, that it will violate the conservation of the charge. Okay. Now next is your Kirchhoff's voltage law. The algebraic sum of the all potential drop and the EMF along any closed path in an electrical network is always zero. That is, total potential drop will be always zero. This is known as Kirchhoff's voltage law. But the thing is that how you will apply in the circuit. See, before that we need to understand that you have to see, you have to you have to use the sign convention. First is that the EMF is taken positive when we traverse from positive to negative terminal. For example, if you are going in a circuit from positive to negative, when you are going from this, so the voltage drop will be plus 5 volt, plus 6 volt, like this. Okay, the EMF is taken as negative when we traverse from negative to positive terminal. If we are going like this, see here, negative, this is your positive, and if we are going in a circuit in this direction, so what will happen? We have to put here minus 5 volt. It is exactly not minus 5 volt, whatever the volt will be given, so you have to put that only. Okay, now if the resistor is being traversed in the direction of the current, the potential difference IR is taken as positive. Okay, what do you mean by this? See here, if R is the resistance and current is I is going and you are also going in this direction, so what will happen? There will be positive voltage drop IR. If current is going like this and resistor is there, but you are going from in opposite direction of current, so it will be negative of IR. Okay, so this is the way to use this. So if the resistor is being traversed in the direction opposite to that current, then potential difference IR is taken as a negative. See here how simple it is. See, if you take this diagram, you use this diagram, right? And we will calculate this. So take an example of A, B, C. And if you travel in this direction, so what will happen? So first drop is what? I am going from this positive to negative. So potential drop E will be taken as positive because we are going from positive to negative. Now see here, the current, we are going in this direction, but the current is coming in opposite direction. So what will happen? It will be minus I1 into R1. Again, we are going in this direction. See here. So the current is I1 plus I2 and resistance support, it is your R2. So the voltage drop will be positive or negative? Definitely negative. Why? Because current is coming in this direction, but we are going in this direction. So what we have to do here? Negative I1 plus I2 into R2. And finally, this should be equal to 0. In this way, we can solve the lots of circuit problem. Okay. See here, for a loop ABC, when we go from this to this direction, see, positive to negative. So we have, this is your E1, and the current is coming in this direction, and this is your R1, and current is your I1. So same thing, whatever I have got, same thing. You have to use this. Okay. Kirchhoff's, see here, Kirchhoff's law, that is Kirchhoff's voltage law, supports the law of conservation of energy. So this should we remember, because if total potential difference will not be zero, then what will happen? Where this potential difference is either going on or coming on. See, whatever energy is being released by this source, so it will be consumed by same amount of the energy by the resistance. If it does not happen, it means that there is a violation of energy law. So that's why we can tell that it follows the current Kirchhoff's voltage law. Okay. Now we will discuss about the Wheatstone bridge. With Wheatstone bridge principle. It is an arrangement of the four resistors used to determine the resistance of the one resistance. See here, the figure, you can see the arrangement. So let us consider P, R and S is known resistance and Q is your unknown. By using this, we'll find the unknown resistance. Okay. So how you will do this? Let us see. Wheatstone bridge consists of four resistors P, Q, R, S. See here, P, Q, R, S with a battery of EMF P. See here, this is your battery of a EMF P. Now on pressing a key of switch on S1 and switch S2, if the galvanometer does not show any deflection, then the Wheatstone bridge is said to be balanced. Here, when you pass the current, you have also passed the current. So what happens? There is no deflection of the galvanometer. That means that there is no passage of the. So this is the situation where we can say that it is your balanced galvanometer. So galvanometer is not showing any deflection. Okay, this means that current is flowing the galvanometer. See here, no current. Current I will become Ig will become 0. That is current through the galvanometer become 0. And the terminal B and D are same potential. See very see. This is your B, this is your D. So if potential, for example, is your 5 volt and this potential is your 5, both have a same potential. So what will happen? If there is same potential, so what will happen? No current will flow because current will only flow if there is a difference in a potential. So here there is possibility of the flow of a current. So galvanometer is not showing any deflection. This means that no current is flowing through the galvanometer and the terminal B and D are at the same place. So this is the method you need to understand why current is not flowing. Now we have to find the condition for the balance Wheatstone bridge. Now for this we have to apply KVL, current Kirchhoff's voltage law to the loop ADBA. See here, this is your A, D, B, A. So we have to use a loop like this. So if you follow this loop, so see here, when we are going in this direction, current is also going in this direction, and this is your resistance. So what will happen? This is the resistance. You can put here. This is not R1, so this will be R only. Okay. So current I2 plus R will be positive because we are going with the current. So the voltage drop will be I2R. And in this area, there is no current is passing. So we don't have to write any voltage drop. But when we are going in this direction, so current is going in this direction. But we are going in this, we are following the path in opposite direction. So what will happen? There will be negative voltage drop. So this will be I1 into minus. The total voltage drop will be 0 as per the Kirchhoff's voltage law. I hope you have understood how to put the values. Now again, so from here what we are getting here, from here we are getting I2 into R is equal to I1 into P. Okay. So this is equation 1. Now again apply Kirchhoff's voltage law to the loop BCDV. See here, we are talking about the other loop that is BCDB. When we talk about this loop, see here, we are going here with the current. So this will be positive. Okay. See, one thing you need to notice here, notice here, or you have to edit here. See, what is the condition? See, if this is your I1, this is I2, so this will be also I1, this will be also current I1, and this will be also current I2. Why I am telling this? Because see here, at this point there is same potential, so it means that there is no difference. So what will happen, current is not being distributed. It means that this current, same amount of current will flow this, whatever current is coming for this wire, so same current will flow with this wire. Okay, so you have to keep these things in a mind. So let us talk here. So from here we have already got this equation. Now again apply KVL loop to the BCDB. So this is your current I1, right? And this is current I2. So from here what we are getting, see here, this is current I1, this is current I1, and this is current I2. So when we are talking about BCDB, 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 when we are talking about the loop BCDB, see here, BCDB, when we are talking about the loop BCDB, so we are going with this current. So, but this current is also I1. Don't consider this at I3. So this will be I1. And we are going with the direction. So there is no negative symbol. So this will be positive. But here what we see, the current that is coming in this direction. So what will happen? See here, but we are coming against the current, so we have to put here negative I2 into S. Here I1 into Q is equal to I2 into S. Now we need to divide this two equations. So when we divide this equation, so what will happen? Rearrange this. See, I1 is equal to I2 into R, and this equation I1 into Q is equal to I2 into S. So from here we can write here P by Q is equal to R by S. So this is the equation we have drawn. It means that when there is a balance condition, so what will happen, if you don't know about the resistors, but you know about the known resistance, P will be the known, Q will be known, S will be known. So you can easily find out this R as an unknown resistance. So this equation gives the balance condition to the bridge. So conclusion, by using this relation, if any resistors is unknown, then we can easily find. Okay. So I hope you have understood how to use the Wheatstone bridge. Okay. So this is all about the chapter current electricity. I hope you have understood this. If you have any doubt, so you can message us. This is the end of the whole chapter. So I will come up with the next chapter, that is moving charges and magnetism. Thank you for watching my video.